So I'm always excited at this part of the semester because we're going to be talking about spectroscopy the whole year. And this one lecture takes you from the spectroscopic image you might get off of a spectrometer all the way down to the wave function. So a lot of courses will start with the wave function, but honestly, that's not how we did this as scientists. We started with the data, and then we pulled the thread mathematically until we got to this weird thing, the wave function. And we said, wow, could this be reality? So we started working with wave functions and predicting the spectra. So that's the way we're going to do this course. We're going to start with what we see with the Blackbody radiation curve, and then we're going to pull that thread all the way through the math that Schrodinger developed, and we'll get to the wave function. So let's jump in. So we have these, did that change automatically? Okay. So we have this quantized idea of nature where we have energy levels and lines. So let's just start with a little bit of vocabulary. This is the idea when we talk about quantized energies, that we have places where the molecule can be energetically, or ion or atom, and places where it can't be. So like right in this region, there's no energy level. And so the molecule, ion, electron, or whatever can't actually have that energy. Now it can on average, if you've got, let's say, 2 up here and 2 right here, the average energy will be right here. But notice how that's an average. If you had four atoms in a bag and you pulled them out and tested their energy, 50% of the time you'd get the high energy one, 50% of the time you get 0. You do the average, you get halfway. But there's no atom in the whole bag that has that energy. So you get some strange effects when you're dealing with quantum mechanics and averages. You get down at the bottom and you're saying, wow, I have this energy, but there are actually no energy levels there. It's just a statistical result. It's kind of like when they say a average family has 1.2 kids. Well, there's no 0.2 kids, right? That's an average. Okay, so you have the same thing happening in quantized energies. Now, when we have these jumps between them, light can be emitted if the electron or the nucleus or atom drops from a higher energy level to a lower energy level. And look at the wavelengths here. They're accurately presented. And so these two energy levels are close together, and so you have a long wavelength. And then this top energy to the bottom energy is really far apart, and so you have a short wavelength. Okay, so that's Planck's equation, right? You have E equals h nu. Okay, so that's how it relates with frequency. And I'm going to teach you something to remember this equation with. So if you're walking down the sidewalk here on campus and someone asks you what's new, you say C over lambda. Okay, and they will know you had me. Okay, so h C over lambda, because that's what's new. Okay, and so you can see that they're inversely proportional. So if the energy level spacing is really big, then the wavelength is really small. If the wavelength is really long, the energy spacing is really small. So light is absorbed, causing arrows to go up. So that's how you can excite the systems. The lowest level is called the ground state. And so these things that are emitted are called spectral lines. And remember from the Bunsen experiment last lecture that went through a monochromator and was on the photographic plate, and you had the slit, and that slit produced lines on the photographic plate. So we still use that term. The lines, spectral lines, are differences in energy levels. You see levels and lines. That's a really important distinction. Those two words you have to keep separate in your mind. Energy levels are the actual levels that the system are in, and lines are always differences. So spectral lines are differences between the energy levels. So up here you have a long wavelength, which means a low frequency and a low energy difference. And then down here at the bottom, you have this one that's a short wavelength, which means a high frequency and a high energy difference. And so all three of these would go through monochromator and be dispersed, and you'd have 3 spectral lines from this emission, because you have 3 different wavelengths. And then you'd have lots of energy areas on that photographic plate where there are no spectral lines. So let's start with the data. That was just some vocabulary. So this is our Blackbody radiation curve. That's the Planck distribution. He solved that using the Boltzmann distribution. And we see this today, this Blackbody color temperature. You see those temperatures on the Planck distribution. You can see that as you get up into the 3000 range, you start to see visible light. But look, it's more red than blue. Very little blue, a fair bit of yellow, and a lot of red. And so this 3000 Kelvin color temperature is actually what we use when we're buying light bulbs, right? 1000, 2000, 3000. That's the Planck temperature that they're talking about. So when you go to Home Depot and you're trying to pick a light bulb, if you like the soft light, the yellowy kind of light, then you need to buy one that has around a 3000 Kelvin figure. And then if you like the really bright, almost blue light, you can go with the 6500s. And so this is right on the side of our little light bulbs that we bought. It had this little spectrum, and I was like, I love that. I'm going to get that for class. So let's take that Blackbody radiation curve, and we can see that in that dashed line, that's the spectrum that we just had, that Blackbody radiation curve. And then what we have below it is a simulation using a 1D particle in a box. And so it's really difficult for us to visualize what's going on in a black body because you have this solid object with lots of atoms and electrons, and they're all moving, and they're in 3 dimensions, and they're absorbing and emitting light, and it's a difficult system to conceptualize. But if you just take a wire and you put an electron on it, a single electron in that wire, it can't leave the wire. You make the barrier at the end an infinite potential so that it can't leave the wire. You have a one-dimensional system, and that electron on that small wire will set up those standing waves, and we'll see that later. So if we simulate this electron on a wire, we can run this all the way up through these equations, and we can get that curve. This one here, the black one. Okay. And so it's a pretty good simulation. Is it perfect? No. There's some line-shaped things that we could do to make it better. But still, it's pretty close. And the reason we do this is because in science, if you can simulate it, then you can understand it. So that's the goal. If you can simulate it, you can understand it. In fact, that's where you can look up on Wikipedia this idea of a spherical cow. Okay, so that's making fun of physicists and physical chemists when they say, okay, how can we simulate these molecules on a surface? Well, it's benzene, right? But we'll say, oh, let's just assume a spherical molecule. Okay, and so they joke about physicists saying, how are you going to model cattle and the way they graze in a field? It's like, well, let's just begin with a spherical cow, right? And see how many cows we can put into this box and so on. So that's what we're doing as scientists, is we're simulating things, and we start with the simplest models that we can start with. And so an electron on a wire, that's a 1D, the wire is one-dimensional, particle in a box. We call that 1D box. It's just a number line. So it's just the x-axis. We put an electron on it. Sounds pretty simple, and yet we can get really close to what the experimental data shows. So let's unpack how we got this simulation. So we're dealing with emission in the Blackbody radiation curve, but here's all the other different types of spectral transitions that we'll cover in this class. So let me show you here. We have these photons coming in. So in each of these little diagrams, time is kind of moving from left to right. And so this wave comes in and hits the particle, and we'll say that the particle is in the ground state, and that particle absorbs that photon of light and ends up in the excited state. And notice this vertical arrow is vertical. It happens simultaneously, like instantaneously. So in time, as we're going along, there's a time when it hasn't been excited, and then all of a sudden there's a time when it's excited. And it's really a discontinuity in time. In fact, it drove Schrodinger crazy. And he's quoted as saying, if we can't get rid of all this damn quantum jumping, I'll be sorry I ever got involved in this mess. And to this day, we still don't know how that happens. We know statistically when it can happen and what we can do to try to make it happen, but we don't know what's going on with this damn quantum jumping. Okay, so there's still some mystery in nature, which is nice. Okay, now emission, this is the one we really can't predict. We've got a happy particle in the excited state, and all of a sudden it just spits out a photon and goes to the ground state. And there doesn't seem to be anything that happens to it. We don't have any sort of thing that tickles our instruments that says, okay, it's about to go. It just goes. We don't know why. Okay, statistically, we can know on average when. And that's, think about nuclear decay. We have an excited nucleus, and it just bursts into particles or spits out alpha particles or splits in two. Okay, we don't have any warning. You know, so we're sitting there looking at, say, a radon atom, and it's going to spit out an alpha particle at some time in its life. Okay, on average, we know that it, I forget what the half-life is, let's say 14 years or something like that. Sometime, you know, half of them will emit in 14 years, but some will last for a century. There's just no predicting when that particular atom is going to fall apart. Okay, so that's spontaneous emission. So you see here, spontaneous emission is C right here, spontaneous. We can sort of tickle that excited state molecule with a photon that matches and cause it to stimulate, emit. So we can stimulate emission, and that's process B. So we hit that excited particle with a photon, and it spits out another photon and drops down. And that's stimulated emission. And that's, of course, it's light, right? So that's radiation. Stimulated emission of radiation. And notice how one photon comes in and two come out. You see that? For stimulated emission, one photon, this is the incoming one, comes in, and then two come out. And they're in phase with each other. It doesn't quite look like they're in phase. I kind of picture them kind of going off at an angle, and then they'll be in phase with each other. So that's amplification. And it's light. So light amplification by stimulated emission of radiation spells laser. And that's how a laser works. So stimulated emission is how a laser works. So those are our emission and absorption phenomena. And then over here we have scattering. Notice in all of these we have a photon coming in and a photon going out. Not so over here. See, over here we have a photon that's absorbed, so we've lost a photon. Here we get some photons. We have amplification of a photon, or we have just the emission of a photon, but here this is scattering. So these three are scattering. And you can kind of look at the wavelengths of the photons and see that this one doesn't change. This is called elastic scattering. So D is elastic scattering. And that's also given the name Rayleigh scattering. So it's strange, if the wavelength of light doesn't change, how do you know something happened? Right? Light comes in, interacts with a particle, and the same wavelength of light is on the other side. How do you know what, if anything, happened at all? It'd be if the photon changes direction. Okay, so it must have hit something. And so this is our scattering that we see that creates a blue sky or a red sunset. Okay, because it's dependent upon wavelength to the fourth power. Okay, so we can understand using Rayleigh scattering where our sunsets and our blue sky comes from. And we'll get into that sometime later. It's in the chapter of my book too, chapter 6. So that's Rayleigh scattering. And also, notice there's a dashed line up here. So, not an energy level. If it matches an energy level, then it's not Rayleigh scattering. I'll just say that. So this has to be off of a resonance. It can't be an energy level. Okay. And these little wiggly lines, that's just to show that this arrow is much longer than it can be displayed on the screen. Okay. So this is typically, a visible or UV light or something like that interacting with a particle. In terms of our our energy levels that we've drawn here. These are, say, visible photons, and these might be infrared energies, and so they're much higher in energy, and they get scattered. And then here's Raman scattering, so inelastic scattering. And we have two types of Raman. We have Stokes Raman and anti-Stokes Raman. And notice it's R-A-M-A-N. It's not the noodles. Okay. So it's not E-N. So when you're writing your reports, don't talk about the noodles. All right, we're talking about Raman spectroscopy. So a photon comes in, it interacts with the system, and it's scattered off. And notice this down arrow is shorter. Okay, so it's inelastic. So the system has more energy than it had before. So the photon gives some energy to the system, and that's Stokes Raman. So the emitted photon is actually the difference between these two. So E equals hc over lambda, and that lambda is long because we've got a smaller energy level difference. And then here we have an excited state particle. Light hits it, causes an oscillation, and then it jumps down to the ground state. So light actually takes away some excess energy. And so it's the incident photon of light plus this energy here makes a new photon that's blue shifted. So this is a red shift, and this is a blue shift. And so those are all the spectroscopic processes we're going to talk about this semester. We'll get into fluorescence and phosphorescence, but those are special cases of emission. And so they're in here too. That's under emission, fluorescence and phosphorescence. And so that's the course. and so we'll go through all of these different things in the infrared spectrum and the UV vis, X-ray. So we'll get into all of the different types of phenomena. But if you can understand the levels and the lines, if you understand the theory behind spectroscopy, then any spectroscopic method you can understand. So you can, if you can draw the energy level diagram and where the arrows are, then you can understand that process. So let's look at the spectrum that comes out of this, okay? So this would be the absorption intensity. Let's just pick absorption, pick that first one. I tried to make it easy to remember. So A for absorption, the total absorption profile, that's the y-axis on a spectrum, okay, is equal to big, B-I-G, the Boltzmann distribution, the intensity calculation, and the Gaussian line shape. And it's the sum of all those transitions. So let's go through all these different variables. Here, n's are your quantum number changes. Quantum numbers, I'll just put Qn. Okay, temperature. This delta lambda is your resolution of your spectrometer. And this is your x-axis. I should say horizontal axis of the spectrum. Let me erase that and see. Okay. So it's basically the intensity at every wavelength. So as you go along the wavelength on your horizontal axis, this is the intensity at that wavelength. So it's a function of wavelength. Does that make sense? All right, so now let's take that. How does that intensity relate to the Boltzmann distribution? The Boltzmann distribution is a function of the quantum number and the temperature. The intensity is a function of the quantum transition, so how the quantum numbers change. And the Gaussian line shape, that has the resolution term in it. And it has the transition wavelength. So let's look at those equations individually. Here's the spectrum. And you see that y-axis is relative absorbance, and this is that result is a sum of all of these pieces as a function of wavelength. Okay, so this curve is right there. And I've plotted the individual pieces of B, I, and G. Okay, you see B is right here, this Boltzmann distribution. It is a factor that gets smaller as wavelength gets smaller. Okay, it's the thermal population of those excited states. And then this intensity equation, this is this little stick right here. See, every one of those has a little stick on it. And then the Gaussian takes that stick and spreads it out. It's the line shape. It's the shape of the spectral line. Everybody see what the Gaussian is? It's the shape of that stick. I mean, our spectra are not just single sticks, right? There's going to be some width to them. Even if there's very little uncertainty as to the transition wavelength, we have an instrument, and our slits are what govern our instrumental resolution. And so if we scan past that, we'll start to see that transition before we're exactly on that wavelength. And so that's what gives us that Gaussian shape. It could be some other function too. There's a Lorentzian and there's a log normal. So there's other kinds of line shape functions. But to keep things simple at the beginning, let's just stick with a Gaussian. It's this sort of statistical normal distribution. So as we get close to that spectral transition, we're going to start to see it. And then when we get right on it, it'll be the maximum. And when we start getting off of it, it'll start tapering off. And so we've just used a Gaussian to model that. Okay, so we'll explore each of those in time. I want to introduce Dirac notation here before we move on, and that is this idea of wave functions, like our particle in a box wave function, times this piece that represents light. Okay. And when we try to calculate that intensity value, that I, okay, it's proportional to this integral. And, you know, people are lazy and chemists are people, okay? And so instead of writing the integral and the limits and the dx, all of this stuff is replaced with these angle brackets. And so this has become this angle bracket here, and this dx has become this angle bracket here. So it's very important for the whole course that when you see these angle brackets, you're looking at an integral, an integration over all space. Okay. Now, when I say all space, it could be in our system just the x-axis, because we're in a one-dimensional system, so that's all space. If you're in a volume like this room, then it's dx, dy, dz. So that would be all space. If you're in a rotational system or a spherical system, you have r, theta, phi. So it's like the distance from the nucleus and then that two angles, like longitude and latitude. So that's Dirac notation. So here are the integrals. That transition moment integral, that's this I piece right here in the middle. These are the intensity probabilities. So the intensity of absorption is proportional to, it's not going to be exactly equal to, but it's proportional to this interaction. We're going to simulate light interacting with our wave function with the x-axis. And so this wave function is a function of x, but then we can also use the x-axis to simulate light. And I'll talk about that a lot more later. Okay, if that kind of confuses you, just think about the x-axis. It has a positive end and a negative end. And the light is an electric field, oscillating electric field. An electric field has a positive piece and a negative piece. And so if our particle is charged in its wave function, and you bring in an electric field with a positive end and a negative end, that particle is going to be perturbed. Okay? It's going to interact with that electric field. And so since the x-axis has a positive end and a negative end, we'll just say that that's how light interacts. So we'll just multiply that wave function by the x-axis, and we get this perturbation that comes from the electric field. Is it exact? No, that's why it's proportional to. Okay, so it's not an exact function. If we wanted to know light, we'd have to put in the magnitude of the electric field and the permittivity of the vacuum and some 4 pi's and things like that, and we get a more accurate prediction of the intensity, but we're just looking at the relative absorbance, and so proportional to is good enough. We don't need to worry about how strong our light is. We just say this is how it would interact. Scattering is a 2-photon process, and so if we have 2 photons, let's just take the x-axis and square it, and that actually works. And so the scattering phenomenon can be modeled by this operator, the x squared operator. That's dealing with the polarizability of the wave function. And so this is what we call the dipole moment. So we'll use x-axis, and that'll be the dipole moment. Let's go ahead and write that down. And this x squared will be the polarizability moment. So this integral squared, we're going to square it because it comes out negative a lot of times. So we'll take this magnitude of this integral, and that is proportional to the absorption intensity. Let's look at the Boltzmann distribution. Okay, this one is kind of interesting. We have this G is the degeneracy of quantum state n. So here we are dealing with the quantum state n. Think about our atomic orbitals for a second, the hydrogenic orbitals. Right, we have the 1s, we have the 2s, and the 2p. What are the 2p? It's got 3 degenerate orbitals. The 1s is singly degenerate, so G equals 1, G equals 1 for that, G equals 3, right? So what do we end up with the 3D up here? We have the 3D, 1, 2, 3, 4, 5, G equals 5. So that's what G is. G is the number of equal energy levels, and so that's the degeneracy factor. This is a 5. It looks like an S. Okay. And now to calculate the Boltzmann distribution, we need to know what the energies are. And so how do we get those energies? Okay. We need to figure out what those are. And then this is Boltzmann's constant. That's nice. This is his distribution, so he gets a constant here. And then temperature. So this is kind of nice. It's taking the energy of that energy level and dividing it by kT. K has the units of joules per Kelvin. So let's write out Boltzmann's constant, 1.38 times 10 to the 20 minus 23, 23rd joule per Kelvin. So notice if I take that and multiply it by temperature in Kelvin, I end up with joules. And so I've taken the ratio of the energy level and another energy. What's that other energy? That's the energy I have in the room. That's the thermal energy. So this is the thermal equilibrium value. So if I take a set of energy levels, this will tell me how many molecules I have in the excited states given room temperature or whatever the temperature of the system is. If I really cool that temperature down, notice it's e to the minus the energy level divided by kT. And if I have a really cold temperature, that's going to be a really small factor. And so I'm not going to have any molecules in the excited state because I don't have enough temperature to get them there. So that's the Boltzmann distribution. Yes. Yeah, that's a good question. It looks like the top of the zero. Okay. Yeah, very good. Let me just make it a little more clear. I've got an eraser on here. Yes. Okay. Okay, good. So the energy levels come from the Schrodinger equation. So this is the energy from this is the Schrodinger equation. It's the integral form of the Schrodinger equation. This is the Hamiltonian operator. And these are the wave functions. And the wave function is the big deal. If you have an accurate wave function that describes your system, then you have accurate energies. Then you have accurate thermal populations. So the wave function is everything. Okay. Wave functions have to be normalized, so we'll discuss this later. This is ortho normality. And you can see, if you read the chapter associated with this set of notes, then you'll see what's going on with orthonormality. And then here's the Hamiltonian operator. It's down here. It's got a potential energy piece. And a kinetic energy piece. And look at this right here, d squared by dx squared. So the second derivative operator. And here's a vocabulary word. So the second derivative is also known as what of the function? Let me back up and do the first derivative. If you were to describe to somebody what the first derivative of a function is telling you, what word would you use that they might know? So if you take the first derivative of a curve at a given point, what are you telling them? That's specific to like motion, but like just of a general curve, like if you're tangent line, which is also what? Slope is the word I'm looking for. So the first derivative is the slope. The second derivative is just the first derivative of the first derivative. So it's the slope of the slope. It's how the slope changes. And so we call that curvature. So the second derivative is curvature. First derivative is slope. Second derivative is curvature. So if I have a curve that looks like this, you see the slope here is changing, here, the slope is, it changes, but not a lot. So it's not very curvy. Compare that to this function. You see this one's more curvy? It's got a higher energy. Because kinetic energy is proportional or equal to that curvature of the wave function. So if a wave function curves a lot, it has a higher kinetic energy. So when you look at a wave function, if you see lots and lots of action, that's a really high energy wave function. If you see almost nothing, like this, that's a really low energy wave function. So I just want visually, I want you to be able to say, oh, okay, I know that wave function is high energy, this one's low energy, and so on. Okay. So here's our wave function for our 1D particle in a box. This is not the only wave function in existence. This is for a specific system. You have wave functions for electrons orbiting nuclei. You have wave functions for the, pi electron cloud and naphthalene. I mean, every different system has a different wave function. But this is the one for the 1D particle in a box. It's a sine. It's a curving function. It's got the x-axis here. Quantum numbers, n. I'm calling it a box in quotes because it's a line. Right. This piece out front is a normalization constant, which we'll explain later. And so you see it's a function, psi, that's our wave function. It's a function of a quantum number and of x. All the others are constants. Pi is a constant, 2, of course, L. You set L for the whole system, and then you can go from there. So let's look at the wave functions for the particle in a box. This is what they look like. I've offset them on the curve according to their kinetic energy. So n equals 1, this is what we have. Not very curvy, is it? And then n equals 2, we have a node here in the middle, and we have 2 lobes. At some time later, they oscillate. So sometime later, it will look like this. Okay. And so let's see if I can switch over to a different scene. And I'm going to turn off the slideshow. Okay, so if I can get a volunteer, come help me. If you'll stand, come forward, and let me go back, and you come forward. There we go. We'll get right at the edges. So this is our ground state wave function. You just hold it as still as possible. I'll be the driver on this. That's our ground state wave function. So in time, that's what it looks like. Okay. Actually, in time, there's an imaginary component too. So if we picture positive imaginary I coming forward and negative I going behind, it's doing this. So in time, it's going from real to imaginary to negative real to negative imaginary. Okay, in time. So when you're thinking, what happens when it's crossing the middle? Does the particle cease to exist? No, it's in the imaginary plane. And then it's in the negative real plane, and then it's in the negative imaginary plane. So it always exists, okay, but it's changing in time. So let's try to do the second excited state. There we go. So it's like that, or maybe like this. There we go. So if you're only looking in the real plane, then you see the real part go up and down. But if you're thinking in terms of imaginary numbers as well, then in time it goes in and out of the imaginary planes as well. It's really unfortunate that they named this square root of -1 imaginary, because it makes it seem not real, So they've really messed. They should never use philosophical terms to label variables, right? Because there's nothing not real about imaginary numbers. Mathematically, they're not real, but philosophically, they're real. Okay, so let that burn your brain cells for a day. Yeah, it was a great car conversation one time. So we said something about taking the square root of a negative number, and my wife's driving, and she goes, "You can't do that." And Katie, my daughter, and my son both majored in math. I'm a physical chemist. Well, all three of us were like, "Yeah, you can." And she goes, "No, you can't." And we're like, "Yeah, you can." She goes, "Okay, what's the result of taking the square root of a negative number?" And all three of us were laughing. We were like, "You get an imaginary number." And she was like, "See, you can't do it." Like, the language was hampering us. She was like, "You made that up." "No, we didn't. You just said it was imaginary." No. So, yeah, you can just picture the psychologist. Is your imaginary number in the room with us right now? So, anyway, there's no way to get around it. So that's our wave function. We don't see the imaginary piece in here because we're dealing with the time-independent system. But when you bring in time, you get Euler's relationship, and it has the imaginary part in it. Okay. And so let's then talk about the horizontal axis in a spectrum. Remember, those spectral lines are differences in energy levels. And so we take a difference, some energy at a higher quantum state, and subtract a lower quantum state. So that's delta E. Delta E equals h nu. And so if you wanted to know the frequency, let's say you plotted that spectrum with the frequency axis instead of energy, then it would just be that change in energy divided by Planck's constant. If you wanted the wavelength of that, then you would invert that, multiply by c, and you get the wavelength. And so this is what we're going to be dealing with mostly, is the wavelength axis, at least in this particular example. And so now we've sort of unpacked everything that went into that experimental spectrum that we started with. We had the Blackbody radiation curve. We showed that the particle in a box can give us a similar looking curve. And then what were the pieces that we used to generate that simulation? We used this overall absorption intensity that was the sum of 3 terms at each wavelength. So we would pick, say, 200 nanometers, and that would be the sum of every one of these transitions smeared out by the Gaussian line shape and added together. And when you add all those together, that's what the sum is, you get this, that point right there at that wavelength. And then you scan the monochromator over another 1/10 of a nanometer, and nature's doing this for you. All of those possible transitions are absorbing the incoming photons, and so that light is missing, and so this is the absorption signal that you see. So this is really representing what's going on in the spectrometer. And why are those transitions happening? Well, they're happening because of the wave functions and light. So light's interacting with the ground state wave function and the upper state wave function, and allowing that particle to hop up there and steal one of those photons of light. And so when we take the I over I naught or whatever and take the minus log of that and get the absorbance intensity or whatever, we end up with this additive signal that's related to the number of photons stolen by our wave functions. Now, how do we know the energies of those? Well, we take the Hamiltonian and multiply by the wave function, and then left multiply and take the integration over all space, and we get those energies. And then those energies are used to create the transition wavelengths. So since we have discrete energy differences, we get single wavelengths at which these transitions occur. And so those wavelength values go here. So this is actually the wavelength of the energy difference from quantum state 1 to quantum state 2. That's where that energy difference is. And that's because our energy equation for this particle in a box goes up as n squared. And then we have 1 over wavelength in there too. We've got a fairly complicated x-axis, but this is where the 1 to 2 transition occurs. This is where the 2 to 3 transition occurs. So this is electrons that are in the second excited state wave function going to the third. And this one would be 3 to 4. And so on. And they get closer and closer together, so it's hard to label them all. Now this longest wavelength one, this lambda 1 to 2, that has a special name. It's called the fundamental. And so that's the first or longest wavelength transition. And it's in the ground state. And in our particular, you'll get into why the ground state is 1 instead of 0 for the particle in a box, but this is the ground state. Okay. And then notice this one starts in state number 2, which would only be there if the system was hot, right? If you cool the system down, all of the electrons are in the ground state and you don't have any of these other peaks. You just have the fundamental. And that's why the fundamental is important. You're always going to have that. Even if you were able to cool this down to absolute 0, you would still have the fundamental. And that's one of your discussion questions, I think, in the second lab. So if you cool it way down, even to absolute 0, you'd still have the fundamental transition. Because these only occur when they're hot, these are all called hot bands. So a series of spectral lines, they called that a band of lines, and so they call these hot bands. So if we can simulate it, we can understand it, and this allows us to understand that blackbody radiation curve. So when we looked at this, if you just looked at this overall intensity, it really looks like you only have 3 peaks. We've got one here, one there, one there. But when you actually look at the spreadsheet that generated this, there's 225 or so different transitions under there. So 200 peaks are underneath those 3 peaks that we see in the visible spectrum. So the visible spectrum can look very simple, but underneath it, it can be very complex. And I think that's good. That's our spectroscopic lesson in terms of the math behind the spectrum. Now, one thing that's missing before you leave is notice we still have these things as integrals. So we really haven't seen the intensity function. And this energy here, these are integrals. And so next week in lab, that's calculus week. Is you will do those integrals. Now they're one dimension, so they're not too bad, okay? But you will do the transition dipole moment integral, which is the more difficult one, and you'll do the Schrodinger equation integral, which is pretty easy. Okay, it's just the second derivative of sine. Okay, not too bad. All right, y'all have a great week.